voltage, and something about the lightning arrestor and BIL. So I'll just very briefly summarize what we discussed in the last class. What we discussed that a lightning can cause a very high over voltage to the insulated string of the transmission line, and this our voltage, though very high in magnitude, but vanishes automatically only in few seconds, few microseconds, and that's why we call it as this voltage is of transient in nature. One difference you must always remember that whenever we say any voltage or any current is transient, what does it mean? That we don't need any action to close it, that means vanish it. It automatically vanishes. The cause is such. So that's why, since the lightning or voltage also vanishes automatically, therefore we call it as transient over voltage. And we also discussed that particularly for voltage system below 220 kV, the lightning over voltage seems dominating. In fact, till now we have discussed only two types of over voltage. One is temporary over voltage and another is lightning over voltage. And comparing in these two, we found that below 220 kV, if we design the insulator for lightning over voltage, it is far greater than whatever the insulation required for temporary over voltage. So that means it is not optimum choice. So also we discussed that since the lightning is a natural phenomena, it cannot be avoided. We cannot stop the lightning. But what we can do is always, this is a principal theory for protection of any equipment, not only the electrical equipment, but any equipment, because it can damage, lightning can damage to other equipment as well, as to divert it through a least impedance path. And how it is done is, this is done by lightning arrestor, as you can see here in this diagram, lightning arrestor. So what the lightning arrestor do is, this whatever is the over voltage here, it drains through this, it drains through this to the ground, and so quick that before the lightning or voltage can cause any damage to the equipment insulation. But once the power voltage vanishes here, then it again come back to its normal situation. That means there will be no current flow through this. So if you just see, like to remember how the lightning arrestor works, just remember, uh, for example, uh, pressure regulator of a pressure cooker. You might have, all of you have seen it. Pressure regulator weight. There is a weight put here, this weight. What's the job of this weight is, once the pressure inside this cooker becomes very high, then it goes upward and releasing the pressure, and as along, after some times, once the pressure inside this cooker becomes normal, then again this weight comes down. Similarly, here, as long as there is a transient over voltage here, as long as this transient voltage is here, conduct, the lightning arrestor conduct, drain that over voltage to the ground, flowing the current. And since this is a transient nature, I have discussed using lightning, it automatically vanishes after some time. And once it vanishes, then this path again becomes a kind of insulator or dielectric, and there will be no flow of current through it. So that's why what we call is the lightning arrestor is only for transient over voltage. It's nothing to, for a sustained voltage. This will never die out. If our voltage of sustained nature, that means continuously, it will never die out. Then this, it will always go on conducting. So that's why the lightning arrestor works only for transient over voltage. And since the lightning over voltage is transient over voltage, that's why it works for that. So that means we also discussed that lightning arrestor should withstand the temporary over voltage. That's why. And for the rating of the lightning arrestor itself is the temporary over voltage rating. For example, for 11 kV, for 11 kV system in Nepal, in all the throughout the Nepal Electricity Authority and other independent power producers and companies, they use it the 10 kilovolt 10 kilovolt lightning arrestor for 11 kV. One of my previous students, they asked me through the messenger that, sir, this is a 11 kV. This is a 11 kV rating, and why we use only the 10 kilovolt lightning arrestor? Isn't it? It's too less. No, it's not less. I have mentioned you in the last class also that whenever we say about the insulation, we should always think about the phase voltage. So since the 11 kV is line voltage, and we think that under the we have discussed that in case of um, a single line to ground fault, or in case of maximum temporary over voltage may be around 80% of the line to line voltage. But again, once we multiply this, this is now the phase voltage, the maximum phase voltage that may occur during the temporary over voltage. And this we have already calculated is around 9.68 kV. That's why we use the 10 kilovolt lightning arrestor. But in some countries, they use for 11 kV itself, they use the lightning arrestor of 12 kV. The lightning arrestor rating for some countries like African countries, or if you go in New Zealand, then you find that the lightning arrestor rating is 12 kV. What does it mean? That they prefer isolated neutral, and therefore in some cases their phase voltage may be equal to the totally full line voltage. So always remember that rated voltage of arrestor is the system temporary over voltage, and hence it depends on the neutral grounding condition. Then we also discussed that there is a, since the lightning arrestor should withstand the temporary over voltage, this what does it mean? That it should not start conducting for a voltage or equivalent voltage for its own rating. It must start conducting something above that voltage, and that voltage may be up to 1.5 times. Again, I mentioned you in last time class also that this does not mean that always it is 1.5 times. Only difference is if you this ratio you make smaller, then the margin, that the safety margin becomes less. And once this 1.5, you say 1.1, I choose. Then what will happen? That there may be a chances that lightning arrestor may operate during the temporary over voltage. But if we consider this too high, as for example 1.5 or 1.6, then what will happen? That if this will be very high, then the voltage at which the lightning arrestor starts conducting becomes increasing, and that means the voltage, even the lightning arrestor starts conducting across that, becomes higher, and the throughout the insulation level should be high. So in short, lower will be this ratio, there may be a chance of lightning arrestor to operate in temporary over voltage. Higher will be this ratio, then the insulation level or insulation cost of the system will become higher. Then we also discussed that this is very important, that is the voltage across of the terminal of the arrestor during the conduction, because all the equipment to be protected by the lightning arrestor must have the insulation level greater than this voltage, because this is the voltage even across the lightning arrestor, even the arrestor is conducting. And we had also discussed that there are factors on which this depends on, and why we call the spark over voltage. It depends on a spark over voltage means, for example, it's always known that for a 11 kV system, for a 11 kV system, say a spark voltage will be less than 132 kV. That's well known. So here Once I'm saying that this residual voltage depends on the scar voltage, my intention is something different. What is that is, even for 11 kV, even for 11 kV. So that's why for a given system voltage, what will be the spark over voltage? Spark over voltage depends on depends on grounding condition or Z0, zero sequence impedance, right? So lower will be the grounding impedance, lower will be the temporary over voltage, and hence lower will be the spark over voltage. Also, we discussed that quality of the lightning arrestor, because whenever there is this lightning arrestor starts conducting, and we discussed that ideal. So say this is over voltage. This is the over voltage. So what it is done is, what happens that during the operation it may start operating at, so lightning arrestor say operates at this point. Then what is ideally we think that it should, the voltage across the lightning arrestor should fix on this, but it is not, because whatever the nonlinear resistor we put it will not be ideally, it will like go than this. So depending on the nonlinear resistance material, this characteristic will differ, and that's why we call it as the quality of arrestor. And basically the two materials used for the lightning arrestors I have mentioned you, that is silicon carbide and zinc oxide. So this is also called the metal oxide arrestor. And also it depends on the system voltage, because lower will be the system voltage, here you can see lower will be the system voltage, higher will be this lightning arrestor current, and once the current will be higher, the voltage will be higher. So all these three factors uh, decides or are responsible or affect the residual voltage of the. So if the equipment to be protected by this arrestor must have the insulation level greater than this residual voltage of the arrestor. But what voltage? Because lightning current do not follow any sinusoidal wave or something like that. So that's why there must be a standard definition that what voltage is equivalent for lightning over voltage, and that's why we also discussed that there is a standard practice. There is a standard practice that the lightning wave is simulated by a standard impulse wave, and that impulse wave is characterized by this. This is the most often you might have seen that this is defined as TF by TT. I have told you that is this TF, or called the front time, or also some people write it TP, is the time for the impulse wave to rise from zero to the peak value. So from here to here, this is TF, this is TF, and this is TT, this is TT is the tail time. So the time to when this lightning falls to the 50% of this peak value. So this, for standard, depending on different standards, this TF may slightly vary. For example, this 1.2 is set for IEC standard, but IEEE standard may consider it as 1. So it slightly differs. So this TF in some standards may vary from 1 to 1.5, whereas this TT is always the 50 microsecond. So this time is in microsecond. Then where were we what when we left it, then what we discussed that the peak value of such wave, this peak value of such type of such standard wave, this which any insulator must withstand, that we called as basic insulation level. Some in some book or some paper you might see that this is also not written as basic insulation level or basic impulse level. In insulation I have written here itself impulse level. Some people also like basic impulse insulation level. So but basically in the beginning it was given name as basic insulation level of the equipment. So what does it mean? That this basic insulation or BIL of any equipment must be greater than the lightning arrestor residual voltage. So that means if anybody now want to set what should be the BIL for a 132 kV system, for example, then what are the criteria or what they will think of? What I mean that since the BIL of any equipment must be greater than lightning arrestor voltage, and once a team of engineers or planners have set together to decide what could be the BIL for a particular voltage, say for example 132 kV, 132 kV, what could be the BIL, most appropriate BIL? They have sit together to fix it. Then definitely what are the considerations they will make? They will make all the considerations is which influence the residual voltage. So that means they will think that what is the grounding condition, what is the grounding practice. Then for this particular voltage, what is the utility, this that utility of course, practice for lightning arrestor quality, which quality of lightning arrestor they use, right? And what is the grounding practice, basically these two. And this may, as I have told you, vary utility to utility, not only utility to utility, but also the voltage to voltage. As we have seen in the last class also, that it is required that for lower is the voltage, best quality of lightning arrestor should be there, because the current flowing through the lightning arrestor is higher in case of lightning strike to the lower voltage. But as the number of equipments in the lower voltage is very high, it's usual practice that lightning arrestor used for the lower voltages of lower quality, just opposite of that. So lower quality means in that case there should have been a sufficient more margin for lower voltage from residual voltage to or sorry, that is the spark over voltage to the BIL rating. So based on the grounding practice and arrestor used for a particular voltage, utility set the BIL for each voltage level. So they have already practiced. Once there is a new standard voltage is now adopted, they again sit and then they discuss that what should be the BIL for this. And one thing is this BIL or basic insulation level or basic impulse level in the same utility at the same voltage also varies from equipment to equipment, and this is called the insulation coordination. What does it mean? That in a system, one one equipment may act as a shield or as a backup for the other. For example, lightning, if you have a lightning arrestor and you have a transformer, right? You have transformer, and you have also say line transmission line insulator transmission line insulator. If you put all these at the same insulation level, what will happen? Once that voltage will reach, this will also fail, this will also fail, this will also fail, and that we don't want. We want that, of course, we want that none of these should fail. But if it is failed, then the first lightning arrestor should fail, because this intention of this lightning arrestor itself is to protect the transformer and line. So first, if it is so, that means BIL of lightning arrestor is least among these three. Then out of transformer and line insulator, if one will fail, if one will fail, then definitely what will be your choice? I think that first transformer, because transformer is at a particular station. Just one point you have to consider repair and other things. But if line insulator will fail, it all along the lines. And that's why in second priority, they give it to the transformer. And then the third is, if fails, then lightning arrestor. What does it mean? That the BIL of lightning arrestor is less than BIL of BIL of transformer, then it is less than the BIL of line insulator. This is basically the insulation coordination, nothing but complex. But once you might be facing difficulty to understand what is insulation coordination, this is the insulation coordination in simplest way, right? So as per, as I have mentioned you several times, that in Nepal we follow mostly all the Indian standards. Our, even we don't have much standard, and even we prepared that standard, it's almost the similar to that of the Indian standard. So as per the Indian standard, they adopt the BIL level for line insulator. This is for line insulator. As I have told you that from equipment to equipment, this BILs should have been different. So this is for line insulator. And uh, last time also I had given you the example that for, if you see the ratio of 11 kV and 132 kV, then the margin in 11 kV is higher than the 132 kV. And the basic reason that here the lightning arrestor quality is lower, and also the lightning current will be higher in case of lower voltage, lower system voltage. So as you can see that here, it has twice two ratings are given. So these are the factors, basically the two factors governing whether this or this, that is the grounding condition and the arrestor material quality used, adopted. But for you as a beginner, you don't worry, you will be given only one voltage. We will provide you that, because later on once you become the professional engineers, then you may get that how the utility said, and in fact the senior engineers, a group of engineers said that what should be the BIL for that particular line. But for you as a beginner, you will be given only one as an practice. So the, what does it mean by now is that for any voltage level, for all the voltage level adopted by that particular utility, they have already the set criteria for the BIL level of line insulator, and once you design this, you will be provided by that. Okay, now let's move to the third and last one, the over voltage. We have discussed the temporary over voltage and what are the factors and how it influences the insulation, then the lightning over voltage and all this. So shortly we should discuss briefly about the switching over voltage also. So as you know that the basic cause in electrical, any electrical circuit, the transient, the basic cause is the energy storing devices, and these energy storing devices in uh, any electrical system is just the inductance and capacitance. In fact, this you know from the very first year of this course itself. And the basic reason why the transient occurs, that this inductance do not allow the change in the current di by dt instantaneously, and this capacitor will do not allow the change in the voltage across it. So what will happen is that once you put a source over it, then the source will try to flow the current here, but it will require some times to that current across this inductor will change, and once it will change, then it will come here, and then again this capacitor will take certain time to charge it, and then it again. So this the flow of, that's why current through the or voltage through the line is in the form of like say a canal water dam. Just at the dam, the gate is just open. So what will happen that if you see that in the below level the water may reach up to far distance, but up above it's coming look like this. So that's why we this is called a kind of traveling. That's why we call that the transient wave along the transmission line will travel. That means but for that this is always true. Any switching condition, whenever we make the switch on, this is always, but often we do not consider it. That's only just if you consider it, then you have to need to think it as a microscopic view. That means you have to limit your time range for very small time. Just if you think in minute or hours, you no need to consider it all these things. So this is the basic reason behind the a transient in any RLC circuit. uh, so basically in power transmission line, the major causes, there are the other causes you might have, that is like say um, in current chopping, ferro resonance, but the basic reason that these things we will study in the uh, high voltage course. But here I'm basically inserting the major cause, and the major cause behind the transmission line over voltage due to switching is the energizing and uploaded. What does it mean? That just switching it on. You have load here. Here you must remember that we are considering the load is at this point. This is the load. This is the load, and we may have another switch here. So this is the load, right? This is the load, and so energizing, this is in fact energizing means you may first connect this and then this, then it will be in the loaded condition. But sometimes it may happen that just you connect this switch but this switch is still off in, that means the load is not there. So what will happen that this current will flow in this circuit. So in second case, now if you say that previously it is connected and now you open it, what will happen? Again, the path of the current will be the same and the over voltage will be the same. So mathematically, though in physically these two are the different action, but mathematically we again need to consider in the same circuit. So mathematically it is same, almost the same. Only may different one difference is that is if the switch has to be on after a long time, then the trap charge across this capacitor may you may not consider. But once you open it, then you must consider the trap charge. What is trap charge? Is like suppose a sinusoidal wave is appeared once the switch as long as the switch was closed. Say for example the switch is closed, right? Then whatever is the voltage across the load is also the voltage across this capacitor. So at a particular instant of time, say the voltage across the load sinusoidal wave was is this much, this voltage, and at this instant of time, this t1, at the same time the switch is open, then what will happen that this voltage will remain across this capacitor, and that we call it v naught. This, so that means this depends upon the trap charge. How much trap charge will be across this capacitor will depends on how, at what instant of time this switching has been done. So it may be the 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 extreme condition could be two, that is this v naught may be either 0, or this may be the maximum value, that is in per unit we call 1, or this may be the another case may be the extreme condition, that is -1. So it could be in between all these three. There will be no other options. All other things will be in between these. So these are the tap charts. Similarly, whenever we energize or de-energize this circuit, then we also here also we have a sinusoidal wave. So whether this switching will occur at this instant of time or this instant of time, or because in this switching either it will be 0 or at t. If you consider at minus, then it will just reverse. That is saying this minus, this plus is same thing. So just either 0 and t. So based on this, in sinusoidal voltage, so you might have studied in circuit analysis, in control system, how to analyze uh, any circuit in as a time domain differential equations format. And you also know that there are classical method and another method is Laplace transform method. So Laplace transform method is becoming easier for us to remember memorize it. And in that case, only difference will, that is, you just write everything in the format of S. That is, so I have already written here. So R is the resistance, Ls is the impedance in the for the inductance in the format of Laplace transform, and this is the admittance form. So I am not devoting much time because these things you know. So this capacitor with a trap charge is an initial charge. You know that for a capacitor has to be modeled as like this. So this you already know, right? So once we say this is equivalent of this, that's why we are considering E, that is the how much current will flow in this depends on what is the in the loop. Just I am using the loop method. So what is the E source voltage minus what is the voltage at this initial voltage, and will be multiplied by the impedance, that is resistance plus Ls plus 1 upon Isc. This is the loop equation, as you know, and from here you can write Ic expression as E minus B naught S upon this is very easy, and you have been encountered with RLC circuit several times. So now, what will be the voltage? What is the voltage we are talking about is what is the voltage at this point? So at this point, the voltage will be, what will be the voltage across this C plus? So voltage eh, during this switching condition across in the line will be equal to the voltage across this capacitor plus the what was the trap charge. This is the trap charge. So trap charge voltage. So from this expression we can find out VCT. How? Because we have the how much is the current. Whatever is the current here is not only the current flowing through the capacitor, the same current is flowing through the inductor as well as resistor. But why we call it as ICS? Because ultimately we have to find VCS, and this VCS is equal to ICS in times 1 upon CS. That's why we call it. So that's not a big difference. So we can write this expression. Yes, this is the from this expression plus this is from the trap charge, that is initial conditions just at the time of what is the voltage across the capacitor at the instant the switching occurs. As you can see that this E is the sinusoidal wave, and a complex mathematics will require to solve this equation. But I have chosen, and you will do it, I hope that, or you might have done it in the high voltage course. But visualizing this, I want to show this in the form of MATLAB. So what I have done in the MATLAB is, as you know that in MATLAB, you can say that this voltage, once you take the Laplace inverse of this, then the in the MATLAB, if you give this as an input and this is the transfer function, means I give a block, and this block has a transfer function of 1 upon RCS plus LCS square plus 1. If the input to this is given as E minus B naught, then what will be the output? Output will be this quantity, right? And if I add this V naught also to this, so if I add V naught is coming here and this quantity is here, this addition plus, then whatever is the voltage we are getting at this point is in fact our the voltage across the capacitor in time domain. And so if I put here a source, this is E is a sinusoidal wave, and one this we can realize that as a step wave, then we may have E minus, this is E, this is V naught, this V naught has to be gone here also, and this V naught has to be, so here I put this as an plus and this as an minus, then here we can get E minus V naught. So this is, I have realized it in the MATLAB Simulink, and just I would like to recall you that, and I want to show you also. So just let's have a look on this. Yes, this is the circuit I have already plotted in the MATLAB. As you can see, as I have told you, this is for source. This is the source E minus. Uh, this is the source wave, and this is for trap charge. And here plus minus you will get here. This is E minus V naught, and this is the transfer function. Yes.
इन्टरप्ट गरेँ। अरूले पनि म्याटल्याबको स्क्रिन नदेखिरहेको हो कि मेरो मात्र हो? मेरोमा पिपिटी नै आइरहेको छ।
मेरोमा पनि
त्यो शेयर गर्दाखेरि तपाईले यो पावर पोइन्ट मात्र शेयर गर्नु।
What happened? Yes. अहिले देख्नुभयो?
सर आयो।
यो मेन पनि आयो कि एउटा मात्रै आयो? एउटा मात्रै आयो? सिमुलिङ वाला यो मात्रै आयो?
हजुर।
यसमा यो प्रब्लम छ। ठिकै, यो यहाँबाट देखाउन गाह्रै होला जस्तो छ त्यसो भए त, किनभने मलाई 3टा स्क्रिन यसमा गर्नु छ। एनीवे, briefly I will say you, and something you may believe me, right? So this is the how I have, and you can do also yourself. This you can make in very simple circuit in the Simulink. So this is the sine wave E, and then this is equivalent for trap charge. This minus this I'm fetching here for this is the transfer function. Then here we'll get the voltage across the capacitor, and if we add this again, this trap charge as we have seen here, then we can get here. This is the, in fact, the voltage, the transient tower voltage. Why I have used this also and this also is just to see in the same graph all the three plot. So I have just first, and what I want to show you in this curve is, I want to show you is for varying the input condition. That means sometimes it may switching maybe at 0 and sometimes at peak, and this the trap charge may be no trap charge or maximum positive or maximum negative. So in fact I have to simulate it 6 in number. So I have already here in the MATLAB want to put the value of R, L and C, and then I would like to simulate it here. So if you see here, what is the, at this instant of time, the phase is at 0. That means the switching instant I have considered is as the 0 value. यो देखिन्छ, यो अहिले यो बक्स एउटा आएछ, देखेछ?
छैन
साइन वेभमा मैले त्यो पनि देखाएको छैन है।
सर तपाईँले सेयर स्क्रिन गर्नु न, अनि सबै स्क्रिन नै सेयर हुन्छ।
सेयर स्क्रिनै गरे जस्तो लाग्छ। सेयर स्क्रिन कहाँबाट हुने? स्क्रिन यो गरेपछि आउँछ। अहिले देखियो?
अब देखियो सर सबै।
ल ल ओके ओके फाइन। So what I mean is this your sine wave. Basically, we are interested on to see that the switch, if what will happen if the switching instant is changing, and what will happen together with the combination of this trap charge. So initially I have considered this as crossing, that is a switching. Once we say that phase is 0 means it start at the 0 value itself, and the for the trap charge I have considered it as one positive value, that is maximum V naught magnitude, as you might have seen here. 1 and 1 means the initial trap charge is the peak value of this sine wave itself. Then what is going to be the result? If you see it, then we will see here, that is we have, this is the actually the sine wave, as you can see, passing through the 0, but now the transient over voltage is very near to the twice of that, 2 per unit, right? So this is the case when we have the switching at the 0 instant and peak of trap charge of positive peak. Now, if I just change it here, just what I have changed, no trap charge. I have applied no trap charge, but the switching instant is again the 0. Now, if you plot, if you run this simulation, you will find that here, see the difference. Without the trap charge, and if the switching instant is 0, there is almost no over voltage. That means the again, even after the, even with the switching, the voltage across the capacitor is 1 pu itself, so no over voltage. What will be the case if we consider the trap charge of, instead of -1, that is opposite of what is the positive peak in case of sinusoidal wave, and then if you run it, you will see that again it is 2 pu. So 3 cases we have seen it, no, from no to 2 pu. Now change one thing, change the switching instant itself, and if I want that this switching instant is at peak value, I can simulate it as by saying that instead of this sine wave, this is the cos wave. So just I put it the phase difference of pi by 2. Then what does it mean? That the sinusoidal wave starts at the peak itself, and that is the switching instant is the peak itself. And what was the trap charge? Trap charge here is initially considered 0, no trap charge, no trap charge, and now plot it. Here again you can see that it is almost the maximum value is again, and you can see that now the sine wave has started at the peak value. Here is the sine wave, and this is the transient voltage is almost 2 pu. This is the case for no trap charge. For positive trap charge, yes, for positive trap charge you can see that again there is no, there is no over voltage. That means it is 1 minus, the voltage is varying from +1 to -1, and the trap charge is the yellow color. Here is the 1 pu. Now consider one more case, that is this trap charge was -1. See the difference. Now the peak value, maximum peak value of this voltage is at almost 3 times of the amplitude, right? If I make for the lossless line, this is, and as you can see that this is dying out. Initially it is very high, then it starting following the sine wave, and later on, as you can expect that after some times it will become only the sinusoidal wave. But what will be the case if I consider the lossless line? And then for that, what I have to make is just make this R equal to 0. I have just make R equal to 0. And see the difference. That means if I make the R equal to 0, that means it is a kind of sustained oscillation. That is oscillations, these oscillations are, this transient is never dying out. And that means the resistance of the line is responsible for dying out. Now, even if you have seen that still, but whether the lossless or lossy line, in case of this is the worst case of, that is the switching is at the peak instant of the sine wave and the trap charge was -1. In that case, the voltage is, the maximum hour voltage is reaching up to 3 pu. You might be conscious that what will happen if I change the L. So whatever L I have used, I want that this L should be half of the L what I have used before, and whatever C I have used, I also want that it should be half of this C2, and then see what is the difference. Is any difference or not? No, just only you see that the frequency of this oscillation transient wave has been changed, but still the peak value is 3 pu. 3 pu, and since this is a lossless line, R we have made 0, so that's why everywhere it is 3 pu. As you can see that it is up to 3 pu. Just even make its double. I make L equals to L times, because half I have already done it, so 4, and C equal to C times 4. Yes, again you can see that now the frequency has been reduced, but still the peak value is. So what's the conclusion I want to draw from this is, from all this, what is our, what conclusion from this wave shape, this simulation work I want to this was our simulation work is, out of just देख्नु भएको छ हैन? हेलो हेलो
हजुर सर देखिरहेको छ
okay. So main हाम्रो, what was our concern is, what will if the switching instant is changing. So switching instant could be either it is the two extreme condition, all the switching instant will be in this between these two, that is peak value or is crossing at the 0 itself. And for each the cases, this trap charge 0, 1 or -1 is relative to the what is the peak value of the sine wave. So then in that conditions we have seen that irrespective of the line parameters, just on depending on the operating conditions, the maximum per unit value voltage change, sometimes no over voltage, no over voltage. If these are the combinations, there is no over voltage. But if this is the condition twice, and if this condition, and the worst condition is mentioned here in the red mark, that is in the worst condition, if the p switching is at peak value and trap charge is negative of the peak value of the sine wave, then the maximum hour voltage due to switching may be up to 3 pu, right? So if just we compute, just now I have computed for the adopted voltage level, like in case of temporary hour voltage or lightning hour voltage. So just how to calculate it? Very easy. One new term come here. This value by which the switching over voltage will be multiple of the its peak value itself is called switching surge ratio. This value, these all are in fact the switching surge ratio, but just we are not considering all these because we have to consider the worst operating condition. So this is the switching surge ratio. So how the switching surge ratio is defined as, this is the times by which the maximum switching over voltage will occur in case of, as a multiple of, as a multiple of um, a system voltage. So how we calculated, just say for example 11 kV, as you can see, just multiply it by 1.1, you will get the max this value, and then what you have to do, you have to find out its peak value. So this is, since this is a line voltage, so divide it by root 3, you will get phase voltage, and multiply it by root 2. Now this is your E, whatever we are considering, because we can never leave this maximum system voltage. So this is the E, what we discussed in last two previous slide and in simulation. This value is the E, right? And depending upon the trap charge condition, this is calculated here. So this is the value here, and now since it will be around 3 times, so the worst case the switching over voltage for 11 kV will be this. So other rows calculations are similar, same, just here instead of 11 it is 33, 33, 33, 66, 66, 66, and so on. Now, so in this way, you can calculate the switching over voltage, the worst case situation of the switching over voltage for any given system voltage, you can calculate it. Right? Now, if we like to compare this, its domination with respect to the lightning hour voltage, then we may need to compare its equivalent lightning voltage. I have mentioned you in 2 class before that same insulator have the different voltage level with a stand capacity depending on what's the time of occurrence of that over voltage. And I have told you that the temporary over voltage sustained it for longer time, so that's why it can sustain very small value of temporary voltage, but it can, because the lightning voltage occurs a smallest time. So lightning occurs around the microsecond, whereas the switching, as you might have seen just now in the simulation, that it switching or voltage lasts along in the order of millisecond. So obviously this millisecond is greater than microsecond. So that's why this is for lightning, this is for lightning, and this is for switching. So if same particular insulator can withstand V1 lightning hour voltage and V2 switching hour voltage, then since this time switching time is higher, that's why its withstand capacity will be lower. That means if the insulator can withstand say 100 kilovolt of lightning voltage, if a insulator can withstand 100 kilovolt of lightning hour voltage, its withstand capacity for switching hour voltage will be lesser than that 100 kilovolt, because the switching hour voltage lasts longer than the lightning hour voltage. So roughly it is a same insulator can withstand 1.3 times greater voltage than the switching hour voltage, right? So since same insulator can withstand more lightning impulse voltage than temporary, this is switching, this is switching, this is switching, temporary hour voltage we have already done it. So this is for switching. Sorry. Also, of course, it is true that it is also for temporary overput, but this is not true in that case. In case this 1.3 is for switching over voltage. So if we calculate its equivalent impulse withstand, so switching over voltage this up to there, and its equivalent impulse voltage, that because I want to compare that how the which will be dominating for which voltage, for whether switching or lightning, then this switching in terms of equivalent impulse withstand, this will be just about 1.3 times greater. Just this column is the multiple of 1.3 times of this. So now if we go back and recall our memory for voltage wise lightning over voltage, and then also compare, this is the calculation just now we have calculated from here to here. And for these voltages, we had already calculated the lightning hour voltage for the case of tower footing resistance range 50 ohm and 70 ohm. There are few conclusions you can draw it from here. Just see before this, from here to here, right? And just see in these two cases. What you can see here is that is at 400 kilovolt, if our system voltage is 400 kilovolt, the maximum lightning hour voltage could be this, that is maybe around 1000 kilovolt. But the equivalent impulse voltage for the switching, this is lesser than this, but its equivalent lightning is, this is greater than this. What does it mean? That at 400 kV, if you design the insulator which can withstand the lightning hour voltage, cannot withstand the switching hour voltage. That means, but if you design an insulator which can withstand the switching hour voltage, will definitely withstand the lightning hour voltage. So, in summary, from this table, what we can say that above 220 kV, and this is just, you can see that this is the benchmark at 220 kV is at the benchmark, and that's why you must, in some books till now you have studied several books of the power system, high voltage and other things. One thing now at this stage I would like to make you, that you might have seen when you define the classification of the voltage level, right? So you call high voltage line, extra high voltage line, ultra high voltage line, and several times you might have the curiosity why this definition changes. The EHV definition, extra high voltage line, we start calling from 220 kV. Right now, by now you might have seen that I have considered you several cases for from the air clearance till today, that there are so many things changing at 220 kilovolt. That's why it is. That means in EHV lines, now you can remember, in EHV lines, in EHV line, switching and temporary over voltage dominates. Whereas for high voltage, the lightning. What will be the case for UHV, ultra high voltage, that is above 765 or something like that? But of course, it will be the similar to the EHV, but there is some special precautions, special provisions are used, and that's why it is called UHV. I will come just after one or two slide that what are those. So above 220 kV, right till now, above 220 kilovolt, switching over voltage dominates over the lightning. And why I have written here the temporary also, because we have already discussed this previously. And if insulation level set to meet full the switching over voltage, say see here the difference now. As the you go on increasing the voltage, as you go on increasing and increasing the system voltage, the discrepancy between the lightning over voltage and the switching over voltage goes on increasing. So as for lower voltage level, if the insulation is designed just to meet the full lightning voltage, it's very costly. Similarly, if the system voltage becomes very high, if the system becomes voltage becomes very high, the switch, if you design a insulator based on the switching over voltage, then the cost becomes very high, and you must have to design it for the switching over voltage. That's why the one other option could be that, if possible, control the switching over voltage. And one of the controlling provision of the switching over voltage is also the lightning arrestor. That's why, because just today in the beginning itself, I have precautiously used one word called, instead of calling it that is the lightning voltage, I called it as the lightning arrestor. Lightning arrestor can work for transient voltage, transient and transient over voltage. And by that time I have hidden this word that since the switching over voltage is also a transient over voltage, so same lightning arrestor, similar nature, it can also work for the switching over voltage. And as I have told you that the switching over voltage also travels along it, so switching over voltage will travel it, but once it will be at this reach at this point and will be the equivalent voltage is greater than the spark over voltage, then it will conduct and it will pass it, and the voltage across the lightning arrestor, which is also the line voltage, phase voltage at this point, is the residual voltage of the lightning arrestor. So lightning, what's the usually we call the lightning arrestor and surge arrestor at relatively lower voltage. Relatively, what does it mean? That, say for example, I am saying that 66 kV in fact is a higher voltage, but I am calling it as lower voltage with respect to, whenever I say high voltage or relatively low, means with respect to, now you should understand that it is for 220 kilovolt. So with respect to 220 kilovolt, it is lower voltage. So at relatively lower voltage, it's mainly for lightning, because the switching over voltage is not dominating by that time. So this lightning arrestor is solely for only for the lightning, and that's why it is called the lightning over voltage. Or also some people call that surge arrestor. One thing I would like to remind you at this stage again, that lightning arrestor is used not only for the electrical equipment protection, but also for non-electrical electric devices. Like for example, protection of a sensitive building against lightning. So what is done is, one spike at the building is done, and then a ground wire, and through ground wire, lightning arrestor is there. So lightning arrestor may be used for protection of non-electrical devices, right? And also for electrical devices. And if you go for EHV lines, this arrestor job is to protect this line from the, or minimize the effect of switching over voltage, so that the insulation level required for the insulator will, for a switching over voltage, could be minimized, and in that case it is called surge arrestor. One thing, that's why if you just compare these two sentences, then also what I can say is, all surge arresters, all surge arresters are lightning arresters, but not all lightning arresters are surge arresters, because lightning arresters vary over wide range. Even you don't have the linear resistance, simple a gap, just a gap, air gap, this is also a lightning arrestor, right? And as I have told you that lightning arresters are also used for protection of non-electrical equipment. So say for example 400 volt protection, system protection, or building protection and others, the lightning arrestor are simply the air gap. But if you go for this, because the switching over voltage, as you have seen that once the system voltage is increasing, is very high, so we have to limit the residual voltage very close to the switching over voltage itself. Oh, sorry, spark over voltage itself, and that's why we require a very high quality material. So mostly the surge arresters are of MOV. This is called that is zinc oxide type, metal oxide metal oxide arrestor or metal oxide barrier. So for residual lower, this is for the surge arrestor. Surge arrestors almost often use the metal oxide arrestor. Again, I will call whenever I call it now the surge arrestor in electrical equipment. It is for protection of both the switching over voltage as well as lightning over voltage. As the in the evolution of the power system, the voltage level of any utility goes on increasing and increasing. That's why the surge arresters is the later name. Previously, at when the system voltage was only up to 220 kilovolt or so, the people call it as lightning arrestor. But later on, it is nowadays it is more popular by surge arrestor. But surge arrestor can protect the system also against the lightning. So, as in case of lightning arrestor, the surge arrestor should also have a, as far as possible, the lower residual voltage, and this lower residual voltage, again we have the same as for the lightning arrestor. It should have good quality material or lower arrestor current. How the lower? This is the arrestor current. This is the arrestor current. As you can see, the last time also during the lightning also we had discussed that how we can make this lower. One is to minimize this itself, and during the lightning that I have told you that during the lightning, this striking voltage could be minimized by using lowering the tower footing resistance. Here we, this lowering of this voltage, this strike voltage, means that minimize the switching over voltage itself. That is, lower arrestor current can be achieved by reducing. This is not what I mean, that just people may think that okay, whatever maybe say 1 million volt or 1000 kilovolt is the switching over voltage. What's wrong? Or 2000 kilovolt is the switching voltage. I have put a lightning arrestor of say 500 kV. It will work because once the voltage at this point, why I am discussing all this, just concentrate what I mean here. What I mean that suppose in a particular system the switching over voltage is 2000 kilovolt, right? And what you think that okay, I have considered like a surge arrestor which will start conducting at 500 kilovolt of impulse voltage, right? Then what's, yes, even it is 2000 kilovolt or 4000 kilovolt, what will happen? This voltage will be 500 kilovolt and we can design the insulation level for 500 kilovolt. No, it's not, because of the practical nonlinear characteristic of the surge arrestor. I have told you that the voltage across during the conduction, which is called the residual voltage, also depends on how much is the current flowing through that arrestor. Larger will be this current, and larger will be the difference from this 500 kilovolt to the another. But this quantity is somewhere proportional to the current through the arrestor. So if this difference, the arrestor voltage and this the striking voltage or the switching or lightning voltage is higher, then it is wiser, even with the lightning arrestor or surge arrestor, to minimize this, because this is the current. Lightning arrestor current is the difference of this voltage minus this voltage the current is flowing. So current should be, to minimize the lightning arrestor current, the switching over voltage itself could be minimized even with the surge arrestor. So lower surge arrestor current can be achieved by reducing the switching over voltage itself, because this is the switching over voltage. This is switching over voltage. So for this to be lower, this must be lower. How this? As I have recently shown you the simulation, what I have shown you there, that without resistor, this transient is never dying out. It's sustained oscillation. But once I have put some resistance, it is dying out. Obviously, That means that if I go on increasing the resistance, if I go on increasing and increasing the resistance, if you say I can justify it as well, otherwise we can move it, because you have also done similar types of simulation in the circuit analysis control system. That is, resistance is act in a RL circuit act as a damping. So if you go on increasing the resistance, the switching or transient is becoming less and less, and that damping coefficient, you if you remember, is expressed by R by 2L, and this denoted by alpha and is given as something multiple and e to the minus alpha. This is the oscillation part, this is the main, the damping part. So even the oscillation is there. If you go on increasing this will die out it very quickly, even it will die out more and more. Okay, let's see one case. If I make this resistance, because we have already the simulation network, so just go on in this and make r equal to say, just before r I would like to again, what was our condition. Just you can see that in whatever the parameter we have chosen, our this is the maximum our voltage was around 3 pu, right? Because we have considered the worst condition of worst condition, that is the trap charge is negative of the maximum peak switching instant value. And so now what we do is make the r equal to whatever was the r. What is the r previously? Just check on. Just check on the r. Okay, it's 0. So I put r equal to now say 100 ohm. Right? R is equal to 100 ohm, and now I am simulating it. And you can see now here the maximum value. Not only the oscillation is dying very fast, but the peak value is also reducing. Previously it was 3 pu, very close to 3 pu. Now I have reduced it to, just by inserting the R, increasing the resistance or of the line, this switching over voltage has been reduced. Now it is nearly 2. So just by adding the just by adding the resistance, the switching over voltage can be reduced by inserting more. But addition of more resistance means more loss, because this is R, L, and C of the line. So if this and this is the source, and we are considering the worst condition of our voltage, that's why we are considering that no load. But once this R is increased, once this R is increased, and this R will, and keep this R also during the operation, then what will happen, that once this switch will close, the current flowing through this becomes very high, and it will cause the I square R loss to be very, very high. But so that's the demerit. But what is here shown here is, because we need the high resistance not throughout, we can, we, even if just during the switching, if we can increase the resistance, we can achieve our work. So what is required for us is, just by inserting the resistance during the switching instant, we can fulfill it, and later on we can disconnect it from the system once the switching has been cleared. So how the arrangement is, this was the previous case. So at across this circuit breaker, this is called the main circuit breaker. What was our main circuit breaker? Across that circuit breaker, we install another circuit breaker, and with a high resistance. This is called RE, is the external resistance. this external resistance, and initially the switching is done just by closing this. So the path of the previous current flow is through this, and once they after as because this transient dies out, then just keeping still this switch on, we make this switch on, and once this switch is also make on, then after a certain time we make this switch off. So this effect is known as resistance switching. Usually for a transmission line, depending on its other parameter values and how much the switching our voltage need to be reduced, the typical value of the resistance, external resistance required here is in the range of 200 to 600 ohm, and it's inserted at around 8 to 10 milliseconds. You might have seen just now I have given simulated for four time period of the 50 for cycle of the 50 hertz system, 0.08, that is 8 millisecond. So it's not needed more than that. So this insertion time is around 8 to or half cycle. You have seen that as the our resistance is increased, it has been the vanished the transient over voltage just even one cycle before one cycle. So 50. After this time, the resistance is short. So what's the procedure is? First, as I have told you, first close the auxiliary circuit breaker. Then this circuit path is like this. Then close the main circuit breaker. This main circuit breaker is closed now. And then after that, open the. So this is the conditions when we are making switching on. But you may have to make the switch off, as in case of previous case. If you want to make this off, then the procedure is just reverse. First, close the auxiliary circuit. Here also you could have a auxiliary circuit breaker. So first, because previously it was closed, so before it's open, just first close this and then open it, and then open this, because once you finally open it, it will be through the large resistance. So but this means that it seems very simple. Why not we do always? It's not so simple, because this 200 ohm and or 600 ohm with that much current which need to be break during on or off, particularly for off condition of making it off, because on you can make even for the no load condition, but off during the off time when you make the circuit off or switching off, the current has to be break very high, and it is called I square RT during the switching. IRT of the switching itself is very high, and you need a high cooling facility, and auxiliary cost becomes very high. Also, you need an auxiliary circuit breaker. So instead of one circuit breaker, now at every point you have to double the cost of the circuit breaker. And circuit breaker cost is, of course, itself is a very higher, and switching heat production is very high, and you should have the appropriate cooling facility for this. But if then is at least you can see that for below 220 kV you don't need at all, isn't it? Because you don't need, because the insulation you design for temporary over voltage or for the lightning over voltage itself will protect the switching over voltage itself. But beyond that you may need it. But if we see very cautiously, then you can think that we may know added advantage, because what does it mean? That we cannot reduce the switching surge ratio below a certain value. There must be a limit. Why it is? Because you have considered no switching surge ratio, you just by increasing this resistance you can achieve theoretically you may achieve SSR equal to say 1. But will we use it? No. Why? Why we cannot use it? In that case, In that case, if you use this switching over voltage and you put a lightning arrestor or surge arrestor, the temporary over voltage itself will be such that. So what I mean that just depending on the grounding condition, what is our requirement for the lightning or surge arrestor? You must remember that it should operate only for the transient over voltage and should not operate for the temporary over voltage. So what I mean that I have given you the hint in the previous classes also. That is what could be the minimum. So what I mean that once you reduce the switching surge ratio, you also need to reduce the temporary over voltage. Otherwise, there is no use. That insulator have the dominating. You reduce the switching surge voltage, but the insulation will be dominated by temporary over voltage. So once the switching over voltage will be reduced, together we should also reduce the temporary over voltage should also for SSR or switching over voltage to be lower requires that the temporary over voltage should also be lower. And how the temporary over voltage will be lower? Temporary over voltage will be lower by reducing the zero sequence impedance. And we have already discussed that even we make the solidly grounded system, we cannot go below that. So since we can achieve the minimum temporary over voltage, minimum temporary over voltage is the phase voltage itself, right? Minimum temporary over voltage is phase voltage. It's so a insulator must withstand this, and if insulator can withstand this value, that means this bp in terms of uh, this bp is the root 2 times of the sorry root 2 times of the b phase rms. That means vll upon vll upon root 3, right? So this is the b peak, b phase, and into the ssr will be your switching over voltage, right? This is the peak voltage, and the ssr is your switching over voltage. And so phase voltage, and as you can see that uh, different over voltage will same insulator can withstand different over voltage. Okay, I am making some bit hurry, so I'm not getting it, but I can give you one thing based on whatever I have discussed with you. You can see that if we reduce this ssr below 2, then there is this below 2 means we are saying that minimum temporary over voltage, minimum when the temporary over voltage will be minimum. So since we cannot reduce the temporary over voltage below the phase voltage, therefore there is no use of reducing this. Two important point I would like to conclude, because I am trying to deliver you many things in short time. So just two things memorize. One thing, both the switching over voltage and temporary over voltage are the system voltage dependent, right? So if the we, in a system we are saying that switching over voltage is increasing because it is a multiple of switching over voltage is a multiple of the system voltage. Temporary over voltage is also the multiple of system voltage. So once the system voltage increases, both are increasing, right? So if you reduce only either of this, the another will be dominating. Hence, once we reduce the switching over voltage, we must reduce also the temporary overvoltage. And since the temporary overvoltage cannot be reduced than 1, and also the same insulator have more capacity to withstand the switching overvoltage than the temporary overvoltage. Therefore, a switching surge ratio below a certain value, just use to why this two if you want to calculate this some typical things I have given you, that just use those. So what you do is, this is your exercise for you. Just what you do is, you find out first the condition for minimum, first point, minimum temporary over voltage. Then find the case that is uh, ratio. Also use the ratio of temporary withstand voltage to impulse withstand. I have mentioned you this. And and third, the switching withstand to impulse withstand. This ratio I have given you temporary 3, roughly 3, right? If I remember, I have already given you in the last class, this is roughly 3, and this today I have given you roughly 1.3. So what does it mean by the temporary to switching is 3 divided by 1.3. So if a insulator can withstand a certain value of voltage V, certain value of voltage V, um, temporary over voltage. If an insulator can withstand temporary over voltage of V, then it can withstand V into 3 by 1.3 times of switching over voltage, right? So based on that, you can conclude. So just recall your memory for this. One is condition for minimum temporary voltage, and then you will see that insulator, if for solidly grounded system, whatever will be the temporary over voltage, if we design an insulator to withstand, yes, another temper. This is the switching over voltage, right? And one thing is, this three ratio I have given you with respect to RMS value, but the switching is with respect to V. So this RMS is to be converted to root 2 time, right? If I do, sorry, 3 and root 2 times will be here. Yes, root 2 will be divided by here. Then you can see that this will be roughly around 2. But just you memorize that switching surge ratio below 2 has no added advantage. So that's why it's not going to be reduced very minimum value. Now with all this, now you can see that for a given voltage, you can, no, just okay, go on sequence. We have several times discussed with you that whenever we design an insulator, it should not only withstand the maximum system voltage continuously, but should also withstand the temporary over voltage, lightning over voltage, and switching over voltage. We have discussed with you now that how to calculate the temporary over voltage, lightning over voltage, and switching over voltage. What should be a insulator for a given system condition? What insulator should withstand what value of temporary over voltage? So we have discussed that given a grounding condition, you can calculate how much uh, insulator for a given voltage should withstand the temporary over voltage. I have also discussed with you that depending on the grounding condition, arrestor quality they use, tower footing resistance they prefer for which type of voltage level, the uh, there is a specified basic insulation level which an insulator of a particular voltage should withstand. So this is also known. This is also known now. Also, based on, if we know the switching surge ratio, as I have told you, that below 220 kV, there the switch, no need to consider the switching surge, but above the 220 kV, the switching surge, the worst condition is 3, and it can be reduced. It can be reduced, but not less than 2. And once we reduce these 3 by the switching surge ratio below 3, we should also reduce the temporary hour voltage. Just by reducing this single is not advantageous. In that case, temporary hour voltage, you know, insulation, I have mentioned you the insulation coordination. In fact, insulation coordination is taught in two terms. One is equipment to equipment, and another is from one type of our voltage to another type. So just this coordinating, this is also a insulation coordination. What should be the temporary hour voltage and what should be the switching hour voltage in optimum manner, so that one is not too far than other, or what should be the BIL setting. All this is also known as the insulation coordination. But anyhow, right now, at this stage, what you can say is we can know, from a given standard and a standard practice of a utility, these three values is known to us. Now, how to check that how much a insulator should withstand a voltage continuously? If you go for this, how to check it? If you check, just try to check this, that insulator, whether it will, what value of this voltage it will, then the life of insulator may be say around 20 to 30 years. So you may have to wait for that. So therefore, this how value is given in the form of accelerated form. So that means what is given, that it will take a long time, as I have told you, to consider. So for a given system voltage, equivalent 1 minute withstand voltage is specified. So what does it mean? That if you know the 132 kilovolt system, then an insulator should be such that it should withstand this maximum value corresponding to this lifelong. But we cannot check it whether it will do or not. So the criteria is converted to 1 minute. So that means then that insulator must withstand more than this 130, that is maximum system voltage corresponding to this, for more 1 minute. And since the insulators, overhead line insulators, are exposed in the free atmosphere, then it's it sometimes it is in dry and sometimes in wet conditions. I have also discussed with you that the creepage path or the flash over distance during the dry condition and during the wet conditions are not the same. So every utility and every following the particular standard specify that what uh, level of voltage should withstand what value of 1 minute dry. So this is for this only. This this is given. So that means now these three, you these you already knowing these three, and for this you use this much. So that means now you have to design an insulator which, for a given voltage, say this is maximum system voltage. What does it mean? That 220 kilovolts, say for example. So 220 kilovolt for continuous maximum voltage withstand, you have to select the insulator which should withstand 430 kilovolt during the dry condition, one minute, and 395 kilovolt voltage during the when the insulator is wet for 1 minute. So you have already two voltage that insulator must withstand, plus this 3, 4, 3, 4, and 5. So that means whenever finally we design the insulator, it should withstand 5 voltage, 1 minute dry withstand voltage is specified. 1 minute wet withstand voltage is specified. The temporary over voltage, the lightning withstand, BIL withstand voltage, and switching withstand voltage. So all the 5 voltage that particular insulator must withstand. So also the manufacturers gives their, based on their material and the shape and size, and as I have told you that their design itself is such that puncture flashover occurs before the puncture. So just for a design engineers for the transmission line, you don't need to consider the puncture. Just consider that for your insulator there should be no flashover. So no flashover this. So what they manufacture based on their shape and size of the different discs, they provide a flashover voltage with respect to number of discs. What does it mean? That, say for example, if they say that if we use my 2 number of this, it can withstand this much one dry 1 minute, this much wait 1 minute, and this much voltage as an impulse voltage. Then first question, how they set it, just I will tell you. But before that, there may be one question in your mind, that why not this flashover voltage is specified only for a single disk, and say for 2 disks it will be twice, 3 disks it will be thrice. Why not it is? It is not. This is because you might have studied in one of some of the course that if, say this is a tower structure, and we have an insulator here. If we use the multiple disk and the conductor is here, in case of multiple disk, the voltage distribution across this insulator, say if this is V1, this is V2, this is V3, this is V4, and the total applied voltage it has to withstand is V, then ideally what is required is that V1 equal to V2 equal to V3 equal to V4, and that is equal to V by 4 times. But this is not this do not happen. What is happen, that the voltage on the lower string is higher than the above and so on. So that means, so what does it mean? That if I say I use 100 kilovolt and the distribution is, say this is 30, this 25, this 20, how much is this? No, say 30, say 35, this is 35, 25, and say 23, and say 22. So if you sum it, it is 400 kilovolt. So, but what is that? If you apply the 100 kilovolt, then one of the insulator has already got the 35. This is just an example, factors 35 kilovolt. So this insulator must withstand this 35 kilovolt. And since it has, and if the one insulator has that capacity, now it cannot, we cannot increase this 100 kilovolt to say that, since one insulator has withstand 35 kilovolt, so why not for 120 kilovolt or 135 into 135 into 4 times this voltage would be. Because if we make this, then the voltage at the lower must may be greater than 35. So as the number of insulator disk in a string goes on increasing, the one term known as string efficiency goes on decreasing. So because of the string efficiency decreasing, you can see in this table that as the number of insulated disc goes on increasing, say for example take 1 and take 8 example, this voltage is not the 8 times of this. And as you go down and down, you will see that this ratio, this is decreasing and decreasing as the number of. So that's why the manufacturer provides this, they based on their test, they have, this is a kind called the routine test. Whenever they manufacture the insulator, they must pass through this test, that there should be no flashover voltage of that insulator should not be, there should be no flashover at 79. If it is at flashover at 85, no problem at this, for this case. So they do it. Now, how to design? How main our objective in the very first class of the insulator design itself, I have mentioned you, that is our main job is for the insulator design is to find out, to compute the number of insulator disc required, number of insulator disc, number of insulator disc for a given system voltage. That is our, just we, this is very simple, just one, our objective is very simple, one. For that, to clarify, we have discussed from last 3-4 classes so many things. So now we are in the position to finally get that what is the appropriate number of insulator discs for a given system voltage. So there are some steps followed based on whatever we have discussed so far. So first what you do is, since in the previous slide we have discussed, in the previous slide, if you go in the previous slide, what we have discussed is, we have discussed that for a given system voltage, for a given system voltage, I repeat, what should be the withstand voltage, what should be the withstand voltage for 1 minute dry, 1 minute wet, representing continuous system voltage. Then what should be the withstand voltage for temporary hour voltage? What should be the withstand voltage for lightning hour voltage? And what should be the withstand voltage for switching hour voltage? Is assuming that these are known to us, but the manufacturer provides the data for the flash hour, not for the withstand voltage. So they give, what is the first job is convert withstand voltage to the equivalent flash over. What do you think? What will be the difference? Which will be lower? Which will be higher? Of course, if an insulator say should withstand 100 kilovolt, if an insulator has to withstand 100 kilovolt, what does it mean? That flash over must be, flash over voltage must be something greater than this 100 kilovolt, isn't it? So this is called flash over to withstand ratio, by the factor by which, this is a kind of informally the safety margin itself. So flash over to, but in a standard, why it is specified that, otherwise people will say that, okay, I will withstand voltage is 100 kilovolt and will, our flash over is at 100.1 kilovolt. So that's why the, when the people make, the people responsible for making the standard, they say no, it's not acceptable. You must have, should have a minimum flash over to withstand ratio. So the times by which this so that means once you know this flash over to withstand ratio, you can convert the withstand voltage level calculated in the previous slide to their equivalent flash over voltage. Also, one thing is, this flash over voltage, whatever the manufacturer specify, is at a given temperature and pressure condition. I hope that you know, familiar with one word called NTP, normal temperature and pressure. This specification is at normal temperature and pressure condition. So based on your atmospheric condition to which your insulator is expected to be exposed, and worst among that you have to consider, that is worst condition, what could be the worst condition. And you know that depend, once the temperature, what is flash over, again I recall your memory, The flashover basically we have defined as the failure of the insulation of the air surrounding the insulator. So that means it is the dielectric, depends on the dielectric strength of the air also. And once the temperature and pressure varies, once the temperature and pressure varies, the dielectric strength of the air changes, and that is called, sometimes you might have used, called air density correction factor. Air density correction factor, you might be know. So here we call it as atmospheric condition. So you have to, first you have to convert to flashover ratio, then you also need to convert it that given the operating worst condition of temperature and pressure, what should be the that value, and then certain factor of safety. So for each of the five withstand voltage we have discussed so far, how to calculate the flashover voltage I am going to discuss with you, because once we calculate that, then from this table we can calculate, use the number of days. So what we do is, so first consider 1 minute dry equivalent test withstand test. So what will be the equivalent flashover for this is 1 minute dry withstand volt for the given system voltage. This is already given in the previous table, I will show you. And then flashover to withstand ratio we have just discussed, then non-atmospheric condition, and then factor of safety. So it will be the, say we have to calculate this for 132 kilovolt, for a 132 kilovolt, then just go on the slide here. In for 132 kilovolt, in 1 minute dry withstand voltage for 130, this is a maximum system voltage. So for maximum, this is a 132 kV system. So it is, that is withstand voltage is 265 kilovolt. So 265 kilovolt. So for 132 kilovolt, this quantity is 100. I forgot what was that. 265. Okay. So 265. 265. So this value is 265. Then you have to multiply this 265 into flashover to withstand ratio, and then the non-atmospheric multiple, and then factor of safety. So say flashover to withstand ratio as per the standard is 1.15, and non-network condition maybe say 1.1, and this factor of safety, this exact value of this data I am just writing approximately will be given you by you to you just now. After this class you will carry out the some numerical exercise in which the Anil sir will provide you the exact value of this ratio we are going to take. But these are in fact the utility practice, it differs. And in fact in true design case, this non-atmospheric condition have to be computed depending on the temperature and pressure, but here you will be specified one value. and and then say the factor of safety, you know that the mechanical engineer or civil engineers take the factor of safety 2 times, 3 times, or so on, but electrical engineers are very conservative in this, in fact and they consider very low values, so maybe 1.1 to 1.2, not more than that. So 1.10, then this is your equivalent voltage. Just this voltage. What you have to do is, for now simply just say this value is, say some value, around this, say I don't know how much it will be because I have no calculation, but say this something is 290 kilovolt. Okay, so for example this calculation is coming as 290 kilovolt. Then what you will do is, just only thing is, just go back in this table and just here see the where is the voltage 290 kilovolt coming in between these two. 290 kilovolt is coming in this two. So now the question is whether you, for that you have the 4 number of disk or 5 number. So here, this is a technical requirement. It is not the optimum only. So you need a insulator which have the flashover voltage of greater than 290. So that's why no choice other than to select this 5 number of this. So what I mean that for just for this case, you will select the number of disks, say, of n1. So n1 number of disk will be selected from here. Next, what you do is just for do the similar process. This is given to you. Then again, this is the flash over to withstand ratio, non-atmospheric condition, and these three will be the same as in the previous case, because non-atmospheric conditions depends on the temperature and pressure. So you are going to design at the same atmosphere, and the factor of safety is your practice. So only thing here and here it will change is, instead of 1 minute dry withstand voltage, you just choose the 1 minute withstand voltage, and then you can calculate and you will get, say, number of disk is 2. Then calculate the temporary over voltage. From the temporary over voltage, the equivalent flash over temporary over voltage, this you already calculated. Say for effective grounding conditions, for example, maybe 0.8 into maximum system voltage. Maximum system voltage, say, just you know how to calculate it. And then again the same factor, this factor is again the same whatever was used previously. So this quantity in fact is same for all, only this first part is going on differing. Then lightning, you know, the you I have already explained you that for a given system voltage, depending on the utility practice, the basic impulse level voltage is already set. So thus just you have a basic impulse level voltage, and then the same as f flash over to withstand ratio, non-atmospheric condition, and factor of safety. And then here, okay, for this, say, n3, and for this, for n5. Now if you go back, to the previous slide, there is no column here how much will be the temporary over voltage. So what you do is, for n3 you use this, because fault can occur even during the wet conditions, and temporary over voltage, assuming that yes, it may along for 1 minute wet condition or so. So n3, for this for n1 you follow this. This will be followed for n2 and n3, and this we are saying for the lightning. So this is for n4. Just follow this column. And then switching over voltage. So switching over voltage you can calculate based upon the set SSR, switching surge ratio. Now, and these three are the same, but one new term comes here. This is called switching to impulse ratio. So sometimes manufacturer, this, as you go back for the manufacturer specification, if they specify only the impulse voltage, if they specify only the impulse voltage, nowadays some manufacturer also specify the basic switching withstand, BSW. But if they have BSL level, sorry, BSL, they specify. But if they not specify, if the manufacturer only specify only the impulse withstand voltage, then what you have to do is, you have to go here, and what you have to do is just convert, because this is the switching over voltage in the order of millisecond, and impulse voltage withstand capacity is for microsecond. So as I have told you that same insulator can withstand more in lightning over voltage or impulse voltage with respect to the switching over voltage. So if only impulse flash over test from the manufacturer is available, then what you do is convert this switching over voltage to the equivalent. So if you multiply these two together, these two together is the gives the equivalent BIL. So here what we are doing, just multiplying by this factor, which is called switching to impulse ratio. We are converting the switching over voltage to equivalent impulse over voltage. So that's why this ratio. And then if we say that this number is N5, now you can use the third column. Now you can use the third column here. This is for N5 as well. So this column is only for N1, this is N2, N3, and this is for N4, N5. So what will be our final number of disks will be maximum of N1, N2, N3, N4, N5 is the final number of disks to be selected. So this all in general about the considerations we make during the insulation design or number of disk selection for the overhead high voltage overhead line transmission line depending on the continuous operating voltage, temporary over voltage, lightning over voltage, switching over voltage. And you know that basically there are so many things before the final steps for the calculation. Here the steps for calculations are not difficult, are very easy, but how to set the temporary over voltage level, or how to set the switching SSR itself, or what's how to select the BIL, these things are, but these are at the higher senior level, these are done at the senior level of engineers. As a beginner, but you should have these ideas, because later on someday you are going to be the senior engineer itself. So, and you have seen that these are not independent to each other. All these three voltages are kept such that one is not far away than the other. Otherwise, the insulation cost has to be increased only for that value. And there is always the control. That's why there is always a control of the lightning and switching over voltage or temporary over voltage needed, and not all the control as is applicable in all the condition. Particularly if we go for high voltage line. High voltage line means not the above 220 kV, you need to control only the lightning hour voltage. Once you control the lightning hour voltage and you design the insulator, it will automatically withstand the temporary hour voltage, switching hour voltage. Whereas if you go for above 220 kilovolt, the switching hour voltage starts dominating the lightning hour voltage, so needs to control the switching surge ratio. However, controlling the switching surge ratio alone or switching hour voltage alone will not work. For that, we also need to control the another system dependent over voltage, and that is called temporary over voltage. So basically what I mean that the system grounding condition not only affecting the temporary over voltage, but also indirectly affecting the lightning over voltage, withstand voltage, and switching withstand voltage as well. So now I am giving you a third assignment. Just what you do is, based on the whatever we have discussed, just if you have forgotten something, you can go back and see the video again and again. And what you have to answer is discuss the role of neutral grounding, that is some people also call system grounding, for the case of temporary over voltage with this temporary over voltage with stand voltage, lightning with stand over voltage, and switching over voltage withstand over voltage. I hope that you understand what I mean. That is, I have already discussed with you that the neutral grounding directly depends on temporary over voltage, but also indirectly the BIL level and switching surge level is set depending on the neutral grounding. Lower will be the neutral grounding impedance, lower will be the BIL also and SSR also. You need to justify these things. And higher will be the grounding, neutral grounding. Your BIL will also increase and your switching surge ratio will also increase. If you able to answer this question, I understand that you will understand whatever we have discussed from last 4 classes. So that's why I am giving you this as a third assignment. No hurry, take your time. And for this time, I would like to ask you to submit this assignment individually, because this is very important part for your understanding of your future career as well. So don't become depend that your friend will do for you. Do just think yourself, whatever you think, write in your own language, not copy. I know that copy paste is possible, but if you do the copy paste, keep these answers separate with you, because I have worked hard to make you understand these complex thing, and I also want that you should understand whatever I have made the effort. So whether you have understood it or not, to check this, I'm giving this assignment. If you have any doubt, you are free to ask me anytime. Even you can ask me directly in call, and my number is 98511638444. But submit this assignment by your own thinking. I will judge that whether you have understood it or not. Thank you. With thanks, now Anil sir will take over.
सर स्लाइडहरू अपलोड गरिदिनु होला सर यसको
हुन्छ, म स्लाइडहरू सबै अपलोड गरिदिन्छु। आज साँझ भरेसम्म म सबै गरिदिन्छु। बाँकी अस्ति त मैले कति